Respected Head of the Department, Dr. V. Kumar Garu, today's guest, Dr. Gopinath Mungala, and my dear participants from various colleges, welcome you all to the two-week faculty development program on application of IoT in mechanical engineering, sponsored by AICTE under Atal scheme. Now we all know that alone mechanical engineering knowledge is not sufficient to lead the industries or to perform academic research. In this aspect, the mechanical department of Prasad V. Potluri Siddhartha Institute of Technology always takes steps to cope up the present things. In line to that, an opportunity is created to uplift the mechanical engineering faculty by including IoT in mechanical engineering. The efforts are recognized and taken in the present shape. To give further details on this, I would like to invite Dr. B. Rakumar sir to address the participant. Thank you, sir. Over to you, sir.
Today's speaker, Dr. M. Gopinath Garu from IIT Hyderabad, and all the learned participants and my dear esteemed colleagues. A very good evening to you all. It's my honor to welcoming you all to the two-week faculty development program on IoT applications in mechanical engineering. As all of you know, this program we are conducting in hybrid mode. The first week we are conducting online, and the second week we are conducting offline. I request all the participants to please utilize this opportunity and attend all the sessions. The Atal this time they are dividing this FDP into three parts. First one is basic mode, second is advanced mode, and third one is institutional building FDPs. Out of which this FDP is in basic mode, wherein the first 1 week is only the theoretical session, and the offline session mostly they concentrated, the FDP wants to concentrate on hands-on experience. So we also planned like that. So during the first week, eminent professors from IITs and NITs like Gopinath sir and all, so they are delivering the basic concept, from the basic concepts to advanced concepts of IoT. In the offline session, we are more concentrating on practical sessions and especially hands-on training. At the end of each session, between offline session and online session, as per the guidelines of Atal, we need to conduct one examination. I request all the participants to please attend that examination, and you need to pass that, you need to clear that exam to get your certificate. And 80% attendance is also mandatory to get the certificate. And I request all the participants to please utilize this opportunity and to improve your theoretical skill and as well as the practical skill in the applications of IoT. And I especially very much thankful because you are accepting our invitation and with a short period, and you are giving the first session on our 15 days faculty development program on IoT. With this small introduction and the instructions from coordinator side, I wish you all the best, and I wish a very happy learned 15 days program for all the participants. Thank you. Thank you, Anand.
I would like to introduce today's chief guest. It's my honor to introduce Dr. Gopinath Mungala to the participant. Dr. Gopinath is currently working as Assistant Professor in the Department of Mechanical and Aerospace Engineering, IIT Hyderabad. He did his PhD and Masters from Indian Institute of Technology, Kharagpur, from the duration 2011 to 2018. He worked as a Senior Scientific Officer for about a year before joining IIT Hyderabad. His current research includes laser material processing, metal additive manufacturing, fusion, and solid state welding, surface engineering, and their real-time monitoring and control. His research innovations and findings are published in various reputed journals and are filed as patents. With this brief introduction, I would like to hand over the session to Dr. Gopinath sir. Over to you, sir.
Yeah, thank you very much, Prashanti, and thank you very much, Dr. Raghu and Dr. Ramakrishna for inviting me for this talk. I will just share my screen and let me know whether it is visible or not. Good evening all. I am Dr. Gopinath. So currently I am working as assistant professor at IIT Hyderabad. So today's my talk will be on monitoring in laser material processing. It comes under the umbrella of IoT in manufacturing, Internet of Things in manufacturing, because we will try to see why this IoT or why Industry 4.0 is needed in the current scenario. First, we will try to see that why Industry 4.0 is necessary and why is everyone running behind that technologies. Okay. After that, we will look into various laser material processings like additive manufacturing, welding, laser forming, and other things, and we will try to see how this monitoring can help you in taking the process to Industry 4.0 level, or how IoT can help you in automating the process. See, whether it is IoT or Industry 4.0, the ultimate task is to decentralize the manufacturing systems. I will tell you what is decentralization, and to automate the manufacturing processes. So the ultimate goal is that, okay, so that the product quality is maintained throughout the process. And now, why are we suddenly worried about Industry 4.0 or maintaining the product quality? Because there are certain products which are existing. Let us say a automobile is existing from ages, right? But now we are all of a sudden interested in Industry 4.0. So what is that particular aspect which is making making it necessary to have Industry 4.0? That we will try to see in the first few slides. So these are the outlines of my presentation. First 1 or 2 slides we will talk about what is IoT and Industry 4.0, or what is the need for it. It's not about what is IoT or what is Industry 4.0. It is about the need for these technologies. And then we will go into additive manufacturing. First we will, in any process, whether it is Industry 4.0 or any kind of automation or control systems, first thing you need to do is understand the process thoroughly. Unless otherwise the process is well understood, you cannot implement any kind of control system. Okay, implementing a control system without understanding the process will lead to nothing, because the control system or the artificial intelligence system, you can call anything in IoT, in Industry 4.0, artificial intelligence, more or less they have some common areas, that is monitoring and control. Okay, so if you want to monitor any process, forget about what kind of process. Okay, today I may be talking about only laser material processing, but remember, whatever technology I talk about can be implemented to any kind of manufacturing process. Okay, so since I work in lasers, I am trying to correlate this IoT with respect to what you call it as lasers, but this can be applied for any kind of manufacturing process. Okay, so first we will talk about need for Industry 4.0, what is the market scenario, and then we will look at additive manufacturing. Within additive manufacturing, first we will try to understand what is laser directed energy deposition and how a monitoring and control system will help you in controlling the quality in additive manufacturing. That we will try to see. So that we will try to see in 3 different aspects, like laser material interaction, process optimization, and then we will try to see how to implement this real-time monitoring in additive manufacturing. So the first 4 points, 1, 2, 3, and 4, typically we try to understand what is this additive manufacturing, what is this LDED, what is anisotropy, and then we will go to real-time monitoring and how to do the real-time monitoring. And once we know how to select the devices for control system, because see, whenever you are talking about Industry 4.0, you want to automate. Now, whenever you want to automate a process, you need to know what are the sensors required to automate the process. Or let us say you are talking about casting. Okay? So what can you monitor? You can monitor temperature. Right? When you talk about forming, you can monitor
ఓకే.
Either deformation,
ఏమనంటే మెసేజ్ పెడుతుండు. ఓకే.
either you can monitor deformation or pressure or the force or even temperature as well. Okay, so once we understand the process, based on the process, let us say you want to monitor the temperature. Again, whenever you want to monitor the temperature, easiest way is thermocouple, right? But a thermocouple is a contact technique, so this you cannot use in automation. Okay, so you need something like non-contact type. So obviously when you say non-contact type, one can say thermal imaging camera. Okay, but whenever you're talking about these kind of thermal imaging cameras, what is its cost? What is its feasibility to apply? So that you need to see. So those are the things which we will discuss here. And now again, when you are talking about these temperatures or the sensors, what are the factors based on which you are going to select that? Okay, just you cannot go and say that give me a thermal imaging camera. You need to know at what wavelength it should operate, or what is the temperature you want to monitor. Corresponding to that, what should be the wavelength, what should be the standoff distance or focal length, what should be the pixel size, and all those things. Now how do we decide? So that is something we will talk about in real-time monitoring, selection of monitoring devices. And then we will try to see one case where this monitoring can be used in additive manufacturing to control or predict waviness. Okay, after that we will also try to see how these monitoring systems can be used in detecting the microstructural changes. Now every one of us know every component that is casted or metal or formed will undergo certain amount of microstructural changes. But is there a way to predict that? So typically what is the procedure? We do the casting, then we cut the sample using wire EDM or wire cut EDM or electric discharge machine, whatever it is. You cut it, then you polish, then etch, and then keep it under SCM. So this is the sequence, and this is a destructive testing because you are cutting the sample. But in an industry, when the process is running, you cannot do all these kind of destructive testing. Now I will show you one way to understand or to predict the microstructural changes in additive manufacturing in a non-destructive way, okay, based on the monitoring systems. And then we will also try to see, to generalize the talk, we will also try to see, based on the availability of time, we will try to see monitoring in laser welding as well as forming or laser forming process. Okay, so these are the outlines of the discussion today. First I will go to a basic introduction, like what is this industry 4.0. So if you see how the industrialization or industrial revolution evolved, so there are things like industry 1.0, 2.0, 3.0 and 4.0. What are we looking at? So industry 3.0 is basically or predominantly came with introduction of automation, computers into manufacturing or computer integrated manufacturing. Now what are we talking about industry 4.0? Decentralized manufacturing. What do you mean by decentralized manufacturing? You will sit at your room, you will make the design of the product, you will send that product over cloud to the manufacturing unit. It may be located within India or outside India, and it can be located anywhere. So you send your design, and then the manufacturing unit will automatically fabricate that product and it will be delivered to you. Okay, so the designer or the customer may not sit in the plant. It's not required. So you can sit anywhere in the world. You can give a command for the manufacturing unit to manufacture a component. Okay,
Oh, sir.
so this is what we are looking at in industry 4.0.
Are you there, sir? In the
So
meeting?
industry 4.0 is a kind of combination of 3.0
Yeah,
as well as
I can see.
this cyber physical systems,
I
that
can
is
see, sir.
decentralized
I can see.
manufacturing. Now why do we need this?
Is it,
Now let us try to see how the
is it clearly
market
visible, sir?
evolved.
The program voice
Okay,
and everything
there are
is
two
coming,
kinds
sir,
of
neatly?
markets. One is push
Fine,
type
sir.
market.
Mm.
Okay,
Mm.
the other one is pull type market. push type and pull
Thank you,
type.
Professor.
Now
Thank
let us
you,
go to couple of
Thank you.
decades
Actually,
back. If you
we
want
thought
to
of,
make any
Dr.
gold
Professor
ornament,
Ramesh Babu is the keynote.
what is the
at
regular
first
procedure?
session.
You used to go to a
But
goldsmith,
suddenly,
tell him your
their close
specifications,
relatives were
your budget,
expired.
and the design you want. You used to explain them,
We
and
immediately
based on
shifted
that,
to,
that
that's why
goldsmith
I
will make
thank
a
you for
particular
short
product
notice
for
we
you.
accept.
Okay,
That's what.
that is craft production, handlooms. Okay, that is a craft
Okay,
production.
Professor, we will meet
So
sir,
this is
on
like a
21st
pull
and,
type market.
we will have
What do you
5
mean
good
by
days.
pull type market?
Coming 5 good
You
days.
understand customers
Hopefully enjoyable days.
need. Based on the
Thank you,
customer's
sir.
need,
Thank
you design the product
Everything is fine now, sir?
and then you sell it to them.
Thank
So
you,
you are
thank you,
pulling
sir.
the customers towards you. Okay, so this is craft production, so which used to be there in 1850s. Okay, so based on individual order, a product used to be made. Then slowly what happened? Industry 1.0 has started, or industrial revolution has started, where automation came into picture. Means kind of mass production, right? So slowly from 1950s, we came into a mass production era with automation, with the advancement of steam engines and other things. Then the moment the
Screenshot
mass
ఇది
production
అక్కడ
came,
మీరు ఉన్నారా?
the market converted
very
into
good,
a
excellent.
push type. What do you mean by push type? You will do a market
నేను
survey
పెట్టేసానులే, నేను
and
రికార్డింగ్
you will make a
నేను
product,
రికార్డింగ్ నువ్వు అక్కడికి స్క్రీన్
okay,
షాట్ చేయి.
which you think is needed for the customer,
స్లైడ్ మారినప్పుడు పెట్టు.
and then you release in the market. Okay, and the customer does not have too many number of choices. He has to buy whatever that is available in the market. Okay, so that is a era. Like let us assume cars. In 1950 you want to buy a car, then only model you available is Ambassador, nothing beyond that. Okay, so if you want to buy a car, you have only Ambassador. That is a push type market. So as a manufacturer, you are pushing something into the market, and the customer is expected to buy that product only, because he don't have too many number of choices. Then slowly what happened, industry 3.0 started gaining popularity, and then what happened, mass customization came into picture. Now what do you mean by mass customization, and what do you mean by mass production? Mass production means you design one product, you produce them in thousands and thousands and thousands of numbers, and then people have to buy that one only. There is no other option for them. When it comes to mass customization, it is slightly different. Here, you will try to understand the needs of the customer, and then you will try to make the component for them. But you will try to make a component for all the customer or large customer base. Okay, so this is what we call it as mass customization. Okay, and then slowly, if you see this curve again in 2000s, okay, when you entered 2000s, you can see that again a pull type market came. What is pull type? Now again, let us assume that you want to buy a car. Now it's no more only Ambassador. You have thousands of varieties, okay, which are getting updated or which are getting modified every 6 months or every 3 months. So what is happening? Companies are reading or taking the feedback from the customers, and based on their needs, based on their taste. Earlier, when you talk about the Ambassador, it used to be in white color only. That was the only color. Slowly black came. So you have 1 or 2 colors. But nowadays, first of all, you have tens and tens of colors available in every car. And even if you want to have a specific color, they can get it done for you. Okay. And then slowly we entered globalization. Okay, no more mass production. It is only pure mass customization or production on demand. Okay, production on demand means you are trying, or let us say you have an Ambassador company. It used to produce like thousands of cars every year, same car. But now the car design is evolving in every 3 months. So whenever the product design is dynamic, means the design keeps on changing in every 3 months. Now what happens or why now you need Industry 4.0 or this automation is, earlier you used to have only one design. If the process is completely automated once, then it will keep on producing it without any deviation. Let us assume that. But now what is happening? In every 3 months, the product is changing. So every time a product changes, the process parameters changes. Every time process parameters changes, the quality or the operating window for a particular process varies. So every 3 months, you cannot sit and optimize your process. So you need some mechanism which can keep monitoring the process and do the changes instantaneously as and when something goes bad. Okay, that is what we call it as artificial intelligence. See, in automation, there is a kind of mechanical automation. So it will keep on, making a component, but it will not bother about what is the quality of each component being made. So what you are supposed to do, you have to monitor each component and try to understand the variations that are coming. Based on those variations or deviations, you need to set the process parameters or change the process parameters instantaneously. No human involvement should be there. The system should be self-dependent or intelligent enough to change those process parameters, right? So that is what we are looking at currently. So due to the large variation in the product design every month or every 3 months, quarterly or half yearly, so you need an automated system which will take care of the production cycle with reduced amount of R&D required for every design. Okay, so this is where the Industry 4.0 is necessary. And one more thing which you have to remember whenever you are talking about manufacturing processes, earlier what used to happen, you used to extract the material or the ore or the source from the earth. It used to go to the manufacturer. Manufacturer used to manufacture the component, and then it used to go to the customer. And once the life is done, it used to go to landfill. Means it goes to the dump yard. Now, if a company follows this particular route, no more the government will allow that company to operate. Now we are looking at circular economy. Everything should be circular. Means whatever you extract, okay, and make a product, it should be reusable, because the population is increasing, the amount of resources nowadays available are very, very limited. Okay, so no more we have a luxury of filling or sending the product for land filling. So as and when you are designing a product, it has to be taken care that it has a it should be it should be in a position to be recycled. Now you talk about the rocket launches. Earlier the rocket launches, as and when they cross the orbit, these rocket launches used to fall into ocean. Okay, we never reused it. But now what we are looking at, the launcher, the thruster takes the rocket or the satellite to the orbit level, and then it is landing back, because now we are looking at reusing those thrusters. Okay, we no more are making them to fall in ocean, rather we are making them land back to the launch pads so that we can reuse it. So at every level we are looking at those things. So this is where again Industry 4.0 is required, because you have to look their operations, you have to monitor its conditions and make sure that these products are not getting damaged. Okay, that is what we call it as circular economy. Now if whatever we talk, if we keep it in a process flow, right? So in every industry, it starts with the process planning. Then assume that we are using an automated system, the part programming will start. Part programming is nothing but set of controls or set of codings you give, so that the tool will follow a particular path for the manufacturing. And then the verification has come into picture. What is this verification? Instead of directly making the component, you first simulate it. Computer aided engineering. First you simulate and see whether the designed product is taking enough loads and other things or not. Okay, and then you have something called as digital twin, because whenever you are talking about Industry 4.0, the first step is to make sure that whatever the instructions that you are giving to a system, okay, are proper and there are no errors in it. Now, how do you do that? So how do you do that? Because then you need a digital twin. Okay, digital twin is nothing but a soft replica of the actual hardware system. Now, just for our understanding, we can see one video over here. Okay, where you will observe that if the part programming is not given properly, what can happen? Okay, you can see these kind of accidents will take place. All these are due to improper part programming. Okay, right? So the command went bad and the tool had hit the workpiece. Now how do you avoid that? So that is where once again you have these digital twins. What is a digital twin? Like I said, it's a soft replica of the hardware. So here you can see the whole manufacturing system is replicated. You can give your program to this digital twin. It will do all the operation that your hardware is going to do, and then any kind of collisions that you can detect at the software level itself before it goes to the a hardware for the production, or before it goes to the production level. So this is once again where Industry 4.0 is required, or where we are looking at digital twins. Okay, because when we are talking about this decentralized manufacturing, okay, so there is a need for a check. Okay, now who is going to check that? Because you are sitting at your home and then you are giving your design and you are sending it to the manufacturing unit and it is automatically taking it, manufacturing it. Then it's a problem. Okay, because if you want to manually check it, then there is no point of again Industry 4.0. That is where digital twins are coming here. So I am not going to talk about digital twin. I hope in the subsequent talks, few more faculty are going to cover it. Okay, then once this digital twin verification is done, it will go to the machine control unit and then manufacturing starts. Okay, but if you see, this complete system is in open loop, means everything is feed forward, nothing is coming backward. Now when you are manufacturing that product, what is the guarantee? Again, we can look at the tool life. Okay, you are using a cutting tool. So when a fresh tool is being used, the surface quality you expect, and as the tool wears out, the surface quality you expect will be completely different. Okay, then who will monitor it and who will instruct when this particular tool has to be changed? So you need a monitoring system. So if you look at a metal cutting operation, dynamometer is one which can give you an estimate of what is happening to the tool life or the tool wear. If the cutting forces are increasing, it signifies that your tool is getting worn out or the tool life has come to an end. The moment the dynamometer reaches to a critical force value, then the machine reads that force and it understands based on the program we have given that the tool life has come to an end, and it will try to change that tool or it will replace the old tool with a new tool. So that is where this condition monitoring and feedback control systems come into picture. Now, today's our topic is predominantly on
admit to deny. దీన్ని అడ్మిట్ మీద తీసుకెళ్ళి నొక్కురా మోస్ట్లీ రారు
condition monitoring, feedback, control systems. So it is like monitoring and control. So would be our topic. Okay. So that is what we call it as adaptive control system. So this open loop and closed loop, this I will skip for time being, considering the Rajesh and Prashanti, they have raised their hands saying that they know it. Okay. So what about the others? Any rough idea? Yeah, I can see few more. So I hope nowadays everyone knows additive manufacturing. So our first topic would be on monitoring and control in additive manufacturing, because I understand that most of the researchers currently are working in this area. So I kept my first topic on additive manufacturing. Followed by that, I will take you to the welding. Now, again in additive manufacturing, I am limiting myself to the metal-based additive manufacturing. Okay, so everyone knows what is additive manufacturing. It is nothing but a layer by layer manufacturing process where, or you can call it as a bottom-up approach, where the component is made in a layer by layer fashion. It's like a building blocks. The way a house is constructed or a wall is constructed, you have an elemental block. Each block is placed one over the other and the wall is constructed. Similarly, if you use the same blocks for a different kind of curvature or the complex shapes, you will be still able to construct it. Okay, assume an complicated structures. So layer by layer, you will be able to realize the structures easily. Now, within additive manufacturing, we have metal-based additive manufacturing. I am only focusing on fusion-based. Okay, there are solid-state welding processes like friction-stir welding, friction-stir additive manufacturing process that I am not considering, but the monitoring part, whatever I am talking here, can be adopted there as well. I will show you one temperature signal, which will give you an understanding about that. Okay. Now, within this fusion-based metal additive manufacturing, we have powder bed fusion process and directed energy deposition process. I will tell you what are those and how do they look like in a very basic way. And then in both these processes, since you are talking about melting of metal, okay, you need some kind of energy source. These energy sources typically used in powder bed fusion are either laser beam or electron beam. But when it comes to DED, along with laser and electron beam, we are also using electric arc. Okay, so this is the classification typically we do when it comes to metal additive manufacturing based on ASTM standards when it is involving a fusion. Means you melt the material and solidify them. Okay, then this is the kind of classification we are talking about. First, we will try to understand this laser directed energy deposition process thoroughly, and then I will take you to the monitor. Now, when it comes to the powder bed fusion process, okay, first thing you need to understand, it is a two-step process. What do you mean by two-step? Now, in a powder bed fusion process, if you look at the system, the hardware of the system, you will have three platforms, okay, or one is the build platform, one is feed container, the other one is the overflow container. What actually you do, if this is your build platform, initially build platform will be at the top. Okay, first what you will do, you will spread a layer of powder of predefined thickness on this build platform. Now how are you doing that? Now you know the area of this build platform. Okay, let us say it is 200 mm by 200 mm platform, and you know the layer thickness what you are targeting at. Let us say you are targeting at 40 micrometer layer pre-placed powder. So based on that, the system will calculate what is the amount of volume of powder required. So this feed container will move up, dispensing this powder out of the container. Okay, a measured quantity, so that this whole build platform can be covered uniformly. Once that is done, this scraper will spread the powder over the build platform. Okay, and typically there is something called as dose factor. Okay, let us assume to cover this build platform of 200 mm by 200 mm with 40 micrometer layer thickness, you require 100 grams of powder. Okay, so what I will do is, instead of 100 grams, I will take 200 grams. Okay, otherwise what happens, if you take exactly 100 grams, which is required to cover this area, then there may be some corners where the powder may not be available, because some powder will automatically come into the overflow container, because uniformly spreading will become difficult. So instead of that, what I will do, I will take a dose factor of 2. What do you mean by this dose factor? So when I require 100 grams of powder to cover this surface, okay, I will take 200 grams, so that I am on safer side and I can ensure that the powder is uniformly spread over this build platform. So typically for the first layer in additive manufacturing using powder bed fusion, we take a dose factor of 5 and above, because the first layer will be very smooth. So if the surface of this build platform is smooth, spreading it uniformly becomes slightly tough. So in order to take care of that, we go with a 5 dose factor. After 1 or 2 layers are deposited, then we will go with a dose factor of 2. Okay, so this is how a powder bed fusion system operates. Now there is something called as laser directed energy deposition process. It is a single step. So what do you mean by single step? Here if you see, the first step is spreading the powder over the build platform. Once the powder is spread, the laser will scan selectively at the locations wherever we need to melt it. Okay, it will not melt the whole build platform. Rather, based on your CAD model, slicing layer, wherever exactly it is required, it will melt over those areas only. Okay. So this is a two-step process. First step, spreading the powder. Second step, melting or selective melting of the powder at the desired location. But when it comes to the laser directed energy deposition process, the powder, instead of being spread, it will be blown through a nozzle. So this is what we call it as cladding head, okay, or DED head. So through this nozzle, the powder will be blown, and from the center of the nozzle, the laser will come. So both the laser and the powder are simultaneously fed, and the moment they come out of the nozzle, they start interacting with each other, and this laser will try to melt this powder, forming a molten pool trap, thereby depositing the material layer by layer. Okay, see, both the process has their own domain in the manufacturing. Okay, so whenever you look at publications, they may say that laser powder bed fusion is better, DED is relatively gives you poor surface finish. But if you want to go for large scale components, or what we call it as big area additive manufacturing or large area additive manufacturing, the only option you have is laser directed energy deposition or directed energy deposition process. But if you have an axiotic structure or a very complex structure, okay, like your medical implants, in those cases, powder bed fusion system is better. Okay, for a small size component having complex shape or complex geometry with where the surface finish should be better, your powder bed fusion is good. Areas or the areas where the size of the component is big. In fact, if you want to refurbish or if you want to repair, you cannot repair a component on powder bed fusion process. You can repair it only in DED process, right? So it has its own domain of applications. Fine. So these are the two processes. Then the next comes the conventional one is the VAM, wire arc. Like I told, whenever we are talking about VAM process, the deposition rates will be extremely high. Okay, so you can deposit a large component very quickly, but that comes at an expense of poor surface finish. So you need post processing. Okay, and then when you do the machining, this is the kind of component you can have. Okay, so just for your understanding, you can see over here, this is the propeller of a ship, and you can see it is 1.3 meters in diameter, 180 kg in weight. Okay, these kind of large components can be manufactured using VAM as well as laser DED as well. Okay, if the surface finish is not of much importance, you can come to VAM. Okay, if surface finish or complexity is slightly high, then laser DED. If it is extremely complex, then powder bed fusion, but powder bed fusion cannot manufacture a 1 meter by 1 meter component. Right now, the technology is available for only 400 mm by 400 mm max. Okay. So these are the limitations of this metal-based additive manufacturing. If you look at selective laser melting or powder bed fusion system, you look at the chamber size. 10 inch by 10 inch by 10 inch or 15.4 by 24 by 19 inch. This is the maximum chamber size that is currently available. Okay, so there you cannot make a rocket nozzle like this, whatever you are looking at. Okay, so if you see these nozzles, these are manufactured using additive manufacturing by NASA. Okay, so if you look at this nozzle size, it is like 90 inch, 46, 70 inch, 56 inch. Okay, so these are all made by DED. When I talk about DED, either it is laser DED or by VAM process. Okay, so this is where we differentiate between the powder bed fusion based on the application and a DED process. Fine. Now let us just go into DED, laser DED process. We will take only one process and then we will try to see how to control it. Okay, so I'm not emphasizing on what is the advantage of additive manufacturing. I hope every one of you know that additive manufacturing is something which gives you a design flexibility. So the main advantage of additive manufacturing is design flexibility. Earlier, there is something called as manufacturability. Whenever you are talking about the traditional machining operations, depending upon the machinability or the accessibility of a particular area for machining, there are constraints on the design of a particular component. But with additive manufacturing, where you are keeping small blocks or the elements and building the final component, those kind of restrictions have reduced. So additive manufacturing offers you wide design flexibility. That is the main advantage of additive manufacturing. So I'm not going into their advantages. Okay, now let us try to understand what is this directed energy deposition process. Many of you might be knowing about this process, but I will try to take you slightly into the depth about the process. Let us try to understand at the elemental level, and then we will go to the next step. Okay, just give me a minute. Now let us try to understand what happens in a DED. So from this schematic, whatever you have seen on the seeing on the extreme left hand side, there is a nozzle. Through the nozzle, the powder is flowing and coming out of the nozzle. Now how does it look like? So this is the video which is showing that you have a nozzle. Through the nozzle, the powder is flowing out. And the most important thing whenever you are talking about this DED process is, the moment the powder comes out of the nozzle, it should focus at a point. It should not just get diverged. If it is getting diverged, then your efficiency of the process will be extremely low. So the nozzle design is also very crucial. Okay. Now, once the powder flow is switched on, then what happens? Next, you are going to switch on the laser. The moment laser is switched on, so you can see the pink color plume over here. This is nothing but laser material interaction zone. Okay. Now both the powder is coming as well as the laser is coming. Both are interacting in this zone where, the interaction starts wherever the powder is getting focused, because it's a halo cone. So at the center of this also laser is coming, but still, since it's a halo cone, the laser and material are not interacting, so you don't see any kind of pink plume. But whenever the powder tends to focus, then it is no more a halo cone, rather than it's a solid cone. So in this location, the laser and powder interacts. Now, why is this important to understand where exactly the laser and material are interacting, or at what location the powder is focusing? Because you can see that you can keep your substrate over here, or over here, or even over here. Now, how do you know where to keep your substrate with respect to the nozzle tip? What we call it as a standoff distance. This should also be fine. This should also be fine, and this should also be fine. But you cannot keep it at whatever distance you want. Typically, we keep it at powder focal point, this one. Okay, because then the catchment efficiency will be more. Does that mean, is it bad? Is it bad? Or is it bad? No, both of them are not bad. You will see when we are talking about the monitoring to control the waviness, that you need this particular standoff distance. Okay, I will show you how it is important, how it is bad for additive manufacturing, but when you talk about control system, how it becomes good, that we will try to see. Okay, now once you understand where the powder is focusing, where the laser material interaction is taking place, then based on that you will decide the location where you are supposed to keep, your substrate. Okay, so you have kept your substrate at the bottom. Okay, so all these three videos are of the same process, and you can see once the substrate is kept, only thing is like you have to understand that this was taken in a monochromatic mode. The first video, second video and third video are in color, but since here there is a lot of light, laser material interaction is taking place, because of IR radiation it is glowing, it's not glowing here, that's it. Okay, so if you see now this layer by layer deposition is continuing, right, and then you will be able to deposit a wall kind of thing like this. So since this is for our experimentation and the mechanical studies, we are not depositing a complex shape, but we do have deposited complex shapes. Okay, so now you see this is like almost like an 100 mm by 100 mm wall, where you can do all kind of tensile testing and other things. Okay, so this is what a TED process looks like, and these are the steps involved in it. Now let us try to understand, when we are talking about this particular video, right, we said laser material is interacting. Now why does it need to interact, and how does it going to affect the quality of your deposition is something which we will try to see quickly. Now if you see, laser is nothing but a light. Assume that you have sun and you have a cloudy day. Okay, so you have a sun and you have clouds in the sky, and assume you are standing over here. Then what happens? The amount of light reaching to you will be very less. You are happy. But in additive manufacturing, the substrate will not be happy, because the substrate need to melt to have a metallurgical bonding. Now, if there is too much of cloud, then the heat will not reach to the substrate. Assume that this man, whoever is standing here, is your substrate. Okay, whatever cloud you are looking at is nothing but a powder cloud. Whatever sun you are looking at is nothing but a laser. Okay, now what happens? This powder cloud density, okay, you can say powder cloud density, defines what is the amount of energy reaching to the substrate. So if the powder cloud density is too high, the whole laser is blocked by the powder. Okay, remember, in additive manufacturing, in TED process, the powder does not melt in air. Most of the people assume that before it reaches to the substrate it is melted. No, it does not happen that way. What happens is, if you have the powder cloud like this, okay, below this assume you have a substrate and the laser is coming like this through the powder. Whatever the light, laser light that passes through this powder cloud creates a molten pool over here. Okay, this powder which has already interacted with the laser gets heated up, but it will not melt. That powder particle will come and sit over here. Okay, now after this instance, what happens? The laser will try to fall on this powder particle which is sitting on this molten pool. So this particular particle is taking now heat from the laser as well as the molten pool from the bottom. So with this heat, it will tend to melt, making a molten pool like this. Okay, so this is how the process happens. Now if you look at this molten pool, whatever initially that was forming because of the laser light that is passing through powder cloud, is acting as a trap for the initial powder particles. Okay, so then only once this molten pool is there, whatever the solid particle is coming, it is getting trapped into this molten pool on the substrate and melting, and due to that melting, this molten pool size is increasing both in terms of width as well as height, trapping more and more powder particles. So this is something which happens at elementary or particle level. One particle after other particle will go into the molten pool, they melt, they increase the molten pool size, and they keep on building a single track. Okay, now what happens is, here we are talking about this trap, or the molten pool on the substrate acts as a trap. Now assume that if this powder cloud density is too high, then what happens? There is no, all the laser energy is blocked by this powder cloud, which are just getting heated up, but they are not melting. Then what happens? You will not be able to establish this molten pool on the substrate, which is acting as a trap for the incoming powder particles, which essentially means this is your substrate, the heated powder particle will come here, and it is being carried by a carrier gas. So it has some inertia at which it is coming. it will just come, since it is in solid state, since the substrate is in solid state, it will just deflect on this direction, on this direction. So ultimately you will not see any kind of deposition. So the first and foremost important thing in additive manufacturing using this LDED is to control this powder cloud density in such a way that there is good amount of substrate melting, which acts as a trap and which also favors in forming a proper clad track. Now, what do you mean by proper clad track? First thing is like you need a trap. Assume that you have a trap. We have a small molten pool. Then I am saying that proper clad track. Now, what do you mean by this proper clad track? Okay, so there should be a critical amount of this molten pool that should be forming on the substrate. Now, why is that required? We will see in the subsequent slides. Okay, so or else I will explain it over here. So now, whenever you talk about the single bead geometry, if any one of you are working in this area or planning to work in this area, this is very important to understand. So a bead can be like this. Okay, a bead can be like this, or a bead can be like this. Okay, here if you see, there is a good amount of deposition with a good amount of metallurgical bonding. Though I am showing it as 50% dilution, 50% melting of substrate, 50% melting of the depositing material, you can assume that this will be typically 20%, this will be 80%. Okay, the way I have drawn it is not proper, but I will show you that. The other way is this one. What is this? This we call it as balling or the balling phenomena. Now in additive manufacturing, you understand that this is the track 1. Okay, next to this you will deposit the track 2. Now this zone is what we call it as shadowed region or the dark region, because now when the laser is trying to fall like this particular bead is actually blocking the laser light from reaching to this location. That is something which will cause or lead to the interrun porosity. So though there was some amount of melting of the substrate, since enough heat did not reach to the substrate, proper wetting will not occur, rather balling will occur. This is not good. Okay, and then if your proper parameters are not controlled, then most of the energy will go into the substrate, melting the substrate excessively. Like let us say 80% substrate is melting and 10% or 20% is deposition. So this is also not good, because you are excessively remelting the substrate or the previous layer. Now, how do we understand what is the amount of energy reaching here? Is not that easy. Okay, because these are what we call it as energy apportionment studies. So you need to understand how to do it. Unless otherwise all these things, you cannot implement any kind of control system, because you need to know what needs to be controlled actually. Is it the laser power? Is it laser scan speed? Or is it the standoff distance? Or it is powder mass flow rate? Or it is laser spot diameter? What you need to control depends upon what is the output or what is the kind of variations you are observing. Unless otherwise you understand the effect of each parameter, you don't know what to control. Okay, so we are trying to understand the process first. Now, how do we know this energy apportionment? So this is where we have developed a new method. Fine, it is good. Throughout the process, till now we are talking about real-time monitoring of temperature, real-time monitoring of temperature. But is it useful to monitor the temperature in additive manufacturing process is a question. So most of us will read in the literature that I am monitoring the temperature, based on this temperature I am assuming these properties are achieved. Is it true? I would say it is false. Those are false claims. Now why I am saying that those are false claims? Okay, now let me try to keep it this way. Now this is a question where all the participants can answer. Okay, assume that I am increasing my laser power in additive manufacturing. Then what happens to the temperature? Participants? Anyone?
Temperature increases.
Increased.
Temperature increases. Perfect. Now I am reducing my velocity. Then what happens to the temperature? Keeping the power.
Temperature also increases.
Temperature also increases. Right? Unfortunately, this will never happen in additive manufacturing. Okay, so this is the problem. This you can only realize if you start working in this area and monitoring. Okay,
Sir, what is the specific reason, sir?
I will tell you. Yes, I will.
Interaction time is increasing.
Yes, no. See, that's what I'm saying. By default, what you said is true. Okay, this is true because you are seeing this Q equal to MCP delta T. Okay. Now what you are doing, you are saying that I am increasing my Q, that the energy input, and obviously my delta T should be increasing. So this is a very well valid answer that the temperature increases in both the cases. But the problem here is we are neglecting this M. Now, if you look at in additive manufacturing, what happens is if you have 100 grams discharge rate, means 100 grams per minute is what your powder feed rate is. Then the catchment efficiency is only 20 gram per minute. What do you mean by that? Out of 100 grams, only 20 grams is getting deposited. Next, remaining 80 grams will just come out of this deposition zone. It will not get deposited. Even if you are achieving 20%, it is a huge achievement. 30% is maximum what we achieve. Beyond that, achieving the catchment efficiency is extremely difficult. Fine, the books suggest that 80% should be the catchment efficiency, 90% should be the catchment efficiency, but experimentally you can never achieve that. Now, let us try to understand what happens. First, we will try to take a remelting case because this additive manufacturing is a slightly complicated case. Now, let us try to understand in case of remelting. Now, you are saying that I am increasing the laser power. Okay. Now, what happens if you increase the laser power? So, let us assume you are using the 100 watt. Then this is the amount of melting you are achieving. If I use 200 watt, this is the kind of melting I am achieving. If I use 300 watt, this is the kind of melt area I am achieving. Now, if you see into this equation, whenever you are increasing the Q, that is input energy, the energy is being consumed in increasing the volume of material being melted rather than increasing the temperature of the same material. So this particular assumption of this, whatever these answers you have given, holds true if in all this 100 degrees centigrade, 100 watt, 200 watt, 300 watt, if the melt volume is same, then your temperature will rise. But now what is happening? With increase in your laser power, okay, the melt volume is increasing. So whatever the excess energy you are giving is consumed in melting the more amount of material. So ultimately what you will observe that is peak temperature will never increase. It will go to a particular value, like let us say if you are doing on stainless steel, assume it's 1560 degrees centigrade is melting point. Maximum surface temperature reaches to 1550 degrees centigrade. And then after that it gets saturated because as you keep on increasing the energy, either by decreasing the scan speed or increasing the laser power, what you will see is that the volume of the material being melted increases, but the temperature remains same. So this is what we have observed, and based on this we have developed certain techniques and we have patented so that a real-time monitoring system can be developed. Okay, so Amile, what I'm trying to say is monitoring the peak temperature in additive manufacturing will be of no use because the amount of material you are melting is very small. So there is a bulk amount of material available below that which can readily melt as and when excess amount of energy is available, so that the energy is being consumed in melting the material rather than raising the temperature of a definite amount of material. Okay, whereas in casting it's different because there you have a definite volume which is melting. So if you keep on giving the energy, the definite volume will melt, boil, vaporize, because beyond that particular volume you don't have any material. But here always there is a substrate which acts like a heat sink and it keeps on taking that energy and keeps on melting. If the whole substrate is melted, okay, assume that you have taken 25 mm by 25 mm by 6 mm thickness substrate. If the whole substrate is melted and still you are pumping the laser energy, then your T will go up. Otherwise it will never go. So this is where most of the monitoring systems and control systems fail. People have reported based on the temperature monitoring systems, but still they fail. So that is where we thought that we should have a monitoring systems which can monitor temperature in a different way. What is that? Now assume that, again, this is a question open to all the audience. This is the substrate. In one case, this is the molten pool size. In the other case, this is the molten pool size. Okay, size 1, size 2. This is very small, this is big. In which of these two cases cooling rate will be high?
S2 case, sir.
Cooling rate. See, this is a smaller
melt pool.
Smaller melt pool. Yes, because smaller melt pool, the heat sink is quite high, whereas here it is bigger, so it will cool slowly. So what I mean by this is, whenever the molten pool size is smaller, the cooling rate will be fast. Whenever the molten pool size is bigger, the cooling rate will be slow. Means your temperature may not vary, but your cooling rates will vary, which essentially means with a change in molten pool dimension or size, your peak temperature may not vary, but cooling rate will give a significant difference, or it will show a change. So based on this logic, what we have tried to do is we try to develop a monitoring system which can detect the cooling rate in real time. So the pyrometers, thermocouples, all these detect peak temperatures or temperature at an instant. But now the target is, how do we detect the cooling rate in real time? Okay. Now, before going into that aspect, first let us try to understand how did we select this pyrometer. That is very important. See, I mean, like, I can tell you that you contact a vendor, you tell him that I want a pyrometer which need to measure from this temperature to this temperature. He will suggest you one, and then you will buy it. But on what basis is he suggesting that particular pyrometer is very important? Unless otherwise you know that, you will buy whatever the vendor is selling to you. So now, what is the logic or what is the philosophy behind selecting a pyrometer? It's simple. Simple Planck's law. Okay, if you take the Planck's law, right, every body in universe above absolute 0 degree temperature emits radiation. Means you are emitting radiation, I am emitting radiation, every body in and around us is emitting radiation. Okay, at its capacity. So that is how, during the COVID time, we have non-contact type IR thermometers which are measuring our temperature, because our body is emitting the radiation. That pyrometer or this thermometer, non-contact type thermometer, is collecting that radiation and converting it into a temperature. Now that is for the body temperature. But if you take the temperature and keep it near a furnace, detector will burn, because it cannot handle it beyond a certain intensity. So all these pyrometers, try to see, I mean, like, you go to any website, either the pyrometer will be able to capture from, let us say, room temperature to 900 degrees centigrade, or something around 400 degrees centigrade to 1600 degrees centigrade, or something around 800 degrees centigrade to 2400 degrees centigrade. You will not see any pyrometer or any thermal imaging camera which can measure from room temperature to 2400 degrees centigrade. These kind of devices are not available. It will be in ranges. So if you are working on friction stir welding, you need this. Okay. If you are working on melting of metals, you need this. If you are melting ceramics or high melting point materials, you need this. But if you want to have one pyrometer which can do everything, that is not available in the market. Now, what is the reason or what is the logic behind that? Just give me a minute. Like I said, every body in universe emits radiation. Okay. Now assume that your molten pool is at 3000 Kelvin. Okay. Sorry, I kept it in Kelvin, so I will talk in Kelvin only. Okay. So assume that there is a body which is at 3000 Kelvin. Now it emits the radiation, but at what wavelength? Whenever we talk about radiation, there should be a wavelength. So it will emit radiation in every possible wavelength. You can see here from 0.5 or let us say 0.3 micrometer to 3 micrometer. Okay, in this whole range it is emitting the radiation like this. This red color line is something which is talking about the intensity, and like x-axis is the wavelength, y-axis is the intensity. Now if you look at this particular body at 3000 Kelvin, it is emitting radiation at every possible wavelength starting from 0.3 micrometer to 3 micrometer. But the intensity of wavelength is maximum at 1 micrometer wavelength. So the moment you ask the supplier that I want to measure the temperature between, let us say, 1000 Kelvin to 3000 Kelvin, he will suggest you this particular wavelength, means a pyrometer or a detector which operates at 1 micrometer wavelength, because here the intensity of IR radiation that is coming is maximum. Now you can obviously ask me, now why is it not measuring lower temperature? Okay, at lower temperature you are talking about this kind of intensity. This intensity is close to zero. So your detector should be extremely sensitive to detect these kind of low intensities, right? So what happens means it cannot measure 25 degrees centigrade, because the amount of the intensity of this particular wavelength at this particular power density is extremely low. So it will not be able to measure. So let us assume if this is the threshold, so it may be able to measure between 3000 Kelvin to 1000 Kelvin, or 1000 Kelvin to 3000 Kelvin. Okay, so that's the reason whenever we talk about any kind of non-contact type of pyrometers or thermal imaging cameras, selection of wavelength is very crucial based on the wavelength. So typically what we do in a different way, we tell the vendor that I need to measure from room temperature to 900. Based on that, he will open this chart, whatever you are seeing on the extreme left side, and then he will say that you need to have a pyrometer which operates at 1 micrometer wavelength. He will give it to you. Now, this is how we select a pyrometer. But there is one problem, or one specific problem when it comes to lasers. So the lasers what you are using are also IR radiation, operating at 1.06 micrometer. Okay, so the IR radiation or the detector which you have designed is detecting the radiation at 1 micrometer from the molten pool. Your laser is also operating at 1 micrometer close to. Then what happens is your pyrometer or your device will essentially detect the laser radiation rather than the molten pool temperature. So you cannot take 1 micrometer. So this is one more problem when it comes to the lasers. So you need to select a device or a pyrometer which operates at a wavelength far from 1 micrometer. So that is where we typically take 1.6 micrometer. Now why 1.6 micrometer? I want to be away from 1 micrometer because that is where my laser operates, but I want to measure temperature between 300 to 1600 degrees centigrade. So this is the optimum wavelength where you can be far away from the laser wavelength, but you will be able to measure up to the melting point. So whenever we buy a pyrometer, this is the physics that is involved behind it. Though we may not know this and we buy a pyrometer, but the one who is selling it to you knows this one, and based on this he suggests. Okay, so this is how we select it. But again, there is a clause here when it comes to lasers. What is that? Now let us say Ambuja cement. So when you look at the advertisement of Ambuja cement, it shows that it is unbreakable. So and then he shows a thief. A thief comes and he tries to hammer the wall and he fails in breaking that wall. Excellent. But if the same thief comes with a bulldozer, will that wall stop him? No, because it has a threshold. It can prevent from a manual damage or a human damage, but it cannot prevent a bulldozer from breaking it. Similarly, every optical device, there is something called as a threshold limit. Okay, so beyond the threshold limit, if you try to give the radiation onto it, it will allow that radiation and ultimately your detector will burn. So now why are we talking about that threshold? Laser is a light. And you know whenever light falls on any object. Now, assume, try to understand how you are able to see a person in front of him. Okay, you switch on the light, right? So the moment you switch on the light, you will be able to see every object inside the room. How are you looking at it? Or how are you able to see it? Because the light falls on the object, gets reflected from the object, that reflected light reaches to your eyes, and then that is how you are able to see that particular object. The important point here is reflection. Light reflects, okay, depending upon whether it is a shiny object, whether it is a dark object, depending upon that, what is the amount of light that is reflecting from that source varies. Now, laser is a light, your substrate is a metal, which will obviously reflect it. So whenever this laser reflects, assume that you are using 100 watt laser power, out of which 10% is getting reflected, which is very low actually. Means 10 watt is reflecting. And this 10 watt will reflect in every possible direction in 360 degrees cone, right? In every direction. And then assume that your detector is here. Out of this 10%, 10 watt, assume that 1% is reaching to your detector, means 1 watt. Your detector capacity will be in millivolt, few millivolts, 0.1 millivolt or 0.5 millivolts is the intensity at which it operates. On such kind of detector, you are allowing a 1 watt laser to fall. Simply it will burn. So when it comes to the laser, off the shelf detectors that are available are now of no use, or of no use. Remember this. Okay. So that is where you have to do something to the existing devices. So you buy a pyrometer which operates at 1.6 micrometer wavelength, that is far from the laser radiation, and then to that you will keep something called as notch filter. Notch filter means, assume that you have constructed a wall out of bricks. Okay, a bulldozer was able to demolish it. Now you give iron steel reinforcement into that wall. Then the bulldozer have to keep extra effort, or the capacity of that bulldozer has to be increased to break that wall. So similarly, the way you are giving the steel reinforcement into the wall, you are giving a notch filter which is like a reinforcement, or which increases the threshold capacity of the detector. Means it will not, if you see this, this is the transmission. So it is transmitting every wavelength, but between 1000 micrometer and 1100 1000 nanometer and 1100 nanometer, then transmission is close to zero. So our laser is operating at 1064 nanometer, which essentially means this particular kind of notch filters will completely block the laser radiation. This is equivalent to giving a reinforcement into a wall. So you are increasing the threshold of your pyrometer. So when you select a pyrometer, or when you select a device, you need to understand the process completely. Now assume that you are not using a laser. Someone may say that, okay, now I am using a wire arc or an electric arc. Then what is the care I am supposed to take? Then you need not need a notch filter, because when it comes to the wire arc, or when you talk about an electric arc, it is a kind of normally distributed intensity like this. So there is no problem with the intensity or the threshold. But the problem is with fumes. So you know that whenever you are doing a welding process, there are a lot of fumes being generated. So if you keep your pyrometer directly there, then the fumes will get deposited onto your lens. The moment fumes deposit onto the lens, its focal length changes and everything gets, or the detector gets bad. Okay. Then what you need to do, instead of a notch filter, you need to give a gas jet such that you prevent those gases from reaching to the detector. So I'm just giving you with process how the detector selection and the care that need to be taken changes. And then when it goes to the furnace, a continuous radiation comes from the furnace. When you talk about VAM, or when you talk about a laser, it is a very tiny heat source. So the amount of heat you feel, because whenever an art process or an additive manufacturing process is taking place, I can stand next to it, but Can you stand next to a blast furnace? No, you cannot stand, because the temperatures next to a blast furnace will be of 100 degrees centigrade or 150 degrees centigrade. So you have to maintain a distance. You can maintain a distance, but the detector cannot be kept far away. It has to be kept close. Then the pyrometers, what we are talking for laser material processing or the VAM process, does not require any kind of cooling system. But the moment you are talking about the casting, now instead of the fume detector or a notch filter, you need a cooling system. See, you see the way the detectors are getting changed with respect to the process. So that's why I'm telling you, in order to buy any kind of detectors or develop a control system, you need to understand the process first. Then only you can buy a detector or buy a monitoring device. So this is how, based on the wavelengths and the temperatures you want to monitor, you can select a pyrometer or a thermal imaging camera. So there is one flexibility in thermal imaging camera. They will come with different kind of filters. Depending upon the filter, again, you can operate for different ranges, but you cannot operate from 0 to 2000 degrees centigrade. It will give you only a particular range. So this is how we select the pyrometers. And the most important point is, all these detectors come in a calibrated way from the factory. Now you bought an off-the-shelf device and you are keeping some filters into it. The moment you keep filters, its calibration is gone. Okay, so all the radiation sensors are calibrated against a black body. So your radiation device is costing you 1 lakh. A black body for calibration system may cost you 1 crore. So you cannot buy a 1 crore calibration system to calibrate a 1 lakh system. So you need to have a robust method or an alternative method to calibrate your device to 12 layers. So from 40 layers to 80 layers to 212 layers, we are able to control the waviness due to heat accumulation and the waviness due to anomalies like oxidation or something else. Okay. Now, if you want to do it in real-time control, because whatever we have done in the previous thing, we are monitoring the process and the human interference is done, means we are intervening in between and we are changing the process parameters. But you want to make it automated, you just attach a displacement sensor like this. Okay. So it will keep on tracking what is the distance between peak and valley, means RZ, let us say. It calculates the RZ. Whenever RZ reaches to the 3 mm or 2 mm or 1 mm, whichever is critical we define, it will set the SOD in such a way that peaks melt, valleys get filled. So this is the technique which we have proposed. We are still working on it. So that's why we don't have result. But the concept is something which we are presenting here. I will just end my talk after this one. So I was talking about the change in microstructure. Now assume that you are making a composite. Okay, composite means, let us say Inconel 718 plus some titanium carbide or tungsten carbide. Now whenever you are introducing the ceramic particles, essentially the ceramic particles should not melt or decompose. This should be embedded into the metal matrix, have some kind of proper tailoring with the matrix, right? Now what happens, which essentially means whenever you are melting this kind of powder, your Inconel, which is metal matrix, melts and the composite or the ceramic particle doesn't melt. So when you look at your time temperature history, the solidification self will correspond to your Inconel 718 only, because your titanium carbide is not melting, so there is no change in the chemical composition, hence there will not be any shift in your solidification self. But assume that you have given lot of molten pool lifetime so that it decomposed. This is the wetting. So this is the cell core structure. So this is the wetting layer. If you give much more time, they will decompose and they will form dendrites. The moment they decompose, the chemical composition of Inconel 718 changes. So no more this solidification self will occur at the same location. So if you see whatever I have represented in the pictorial way, you can see over here, the wetting has started, and as the molten pool lifetime increases, proper shell core structure has formed in these two. But beyond this particular molten pool lifetime, if you extend it further, you can see the decomposition of the ceramic particle is happening and the dendritic structure is forming. And if you continue further, the whole ceramic particles will decompose and then you will have a ceramic dendritic structure like this. So all these dendrite structure, what you are saying, are ceramic in nature, making the material brittle and changing the chemical composition of the material. So based on that, you can understand that if the solidification self location of Inconel 718 and titanium carbide mixture is at the same location as that of Inconel 718, then your powder particles or the ceramic particles did not decompose and have good wettability with the matrix. But if that shifts, then your powder particles, titanium carbide particles, might have decomposed and the chemical composition might have changed. This is not good. See, you are not, so initially you have cut the samples and you have developed this kind of process map. Now, after that, once the process starts in the industry, just by looking at this signals, you can say what is happening inside the material without cutting it. Okay, so that's why I named it as detecting the microstructure in a non-destructive way. Okay, so this is how it looks like. So if you see, the moment the molten pool or the solidification self location has shifted from this point to this point, this is how the microstructure has varied. Whereas in this case, that is not happened. Okay, these powder particles are really intact. Fine. So this is the way you can do it. Okay, so I will stop it here. Fine. So you might, so what we have discussed, we try to understand the need for industry 4.0 or IoT, because we are in a pull type market, or we are in a mass customization where the product has to be designed as per the taste of the customer, which essentially means the variation in the product is quite high. So we need a robust system which can handle all those kind of changes. For that, we need some kind of detectors. And when it comes to the detectors, we limited ourselves to the laser material processing. But remember, anywhere where heat is involved, this pyrometer technique can be used, whether it is friction stir welding, casting, forming, anywhere heat is involved, these techniques can be well utilized. Okay, and then we have seen different kind of technologies or monitoring systems or control systems, where how to select the monitoring system, on what basis it has to be selected, and how to modify them, and how to modify the technique of monitoring, like instead of peak temperature, how to monitor cooling rates. So since it is melting and solidification, I have taken the cooling rate. In some other case, you may need something else. So you have to change the parameter which you are monitoring. So just monitoring the peak temperature always will not give you fruitful result. Sometimes you may have to monitor the temperature gradient. Sometimes you may have to monitor the cooling rates and other things. So the techniques are quite diversified depending upon the process. But as long as you understand the fundamental of the process which you are looking at, you will be able to select one. Okay. So this is where I will stop my talk. Okay. And if you have any kind of queries, I will be happy to answer. Yeah. So any doubts from the participants?
Sir, I have a doubt related to anisotropic nature of the material.
Okay.
You said that killing the anisotropic nature, you have suggested some points and you have shown some results. So that means killing the anisotropic means we are bringing the material to orthotropic or fully isotropic or quasi-isotropic.
Just give a minute. Just again, it got stopped because there's a video.
ఇది మ్యూట్ లోనే ఉంది.
No, see, what we are trying to do in this case is, we are trying to mold the microstructure in such a way that, what you say, the microstructure is no more directional. Okay, the moment it is not directional, okay, so the properties in all the directions will be same. That's it. Okay.
Yes, sir. That means nearly isotropic.
Yes, nearly. Okay, you cannot make it purely, but you can reach to a location where it's near to. Okay.
Okay, sir. Okay, thank you, sir.
So there are certain in the chat box. There are some things. Okay. Oh, sorry. Yeah. questions from the participants? So will you provide the soft copy of this session? Like I said, these are data which are unpublished. You can see in my first slides, these are the students who are working. So unless otherwise the students publish, I cannot share it. But I can provide you the material where you can get data related in this direction. This is to address the comment from Narendra. Yeah, any other doubts, students or participants? Because I can see there are a lot of doctors. Fine, Dr. Raghu or Ramakrishna, yes. It seems there are no questions from the participants.
Yes, sir. Yes, sir. Sir, thank you very much, sir, for your.
Thank you, sir. On behalf of the department, I would like to thank you for giving such a wonderful lecture on IoT in manufacturing. From starting slide, that is need of Industry 4.0 pyrometer selection, and the last topic, that is related to ceramic composites. We have given a very wonderful inputs on this topic. Those who wish to do research on additive manufacturing, so you have shown the path, so they directly can go through on that path. That we know that it takes years of research and continuous efforts to bring this work foot forward to the participants. So thank you very much, sir, for giving this wonderful opportunity and giving
I would add one
precious
point.
time. Thank you, sir.
Yeah, thank you. So I would like to add one point. The data which you are seeing over here was developed over 8 years, by the way. It's not in a year or two. Okay.
Yes,
Because
sir.
8 years.
Yes, sir.
Okay. Fine. Thank you very much. Thank you very much, Dr. Raghu and Dr. Ramakrishna, for inviting me for this talk.
Sir, thank you very much, sir. Thank you very much for your excellent and seamless presentation. Continuously 2.5 hours, you were continuously delivered a wonderful lecture, sir. And it is an excellent session for our beginning session for our IoT. Started with IoT 4.02. You covered one of the application of IoT, that is laser machining, and also then additive manufacturing. You covered most of the topics of Industry 4.0. Thank you very much, sir.
Thank you.
I request, sir, thank you, sir. Now I request all the participants, please fill the feedback form that is available in the chat box. My co-convener, Dr. Ramakrishna, has given that link. I request all the participants to please join tomorrow at sharp at 6:45. All the speakers are we selected from IITs and NITs. They will start exactly at 7. So sharply, I request all the participants to please join by 6:45.